Okay, so think about this for a second. Have you ever wondered how Python, a language literally famous for its simplicity, can effortlessly manage, process, and analyze millions of pieces of data in a fraction of a second? How does it keep track of endless user accounts, massive scientific measurements, or super complex financial ledgers without so much as breaking a sweat? Well, let's dive right into this, because the answer actually lies in the incredibly elegant architecture of its data structures.
Welcome to The Explainer. Today, we're popping the lid right off the Python data toolbox. If you want to write efficient, genuinely powerful code, understanding how to store and manipulate your data is absolutely essential. We're going to explore Python's dynamic data structures, specifically focusing on how lists and tuples act as this incredibly versatile toolkit for literally any programmer.
Here is our roadmap for today. First, the Python sequence, then navigating and slicing data, followed by the list manipulation toolkit, processing real-world data, and finally, going 2D with nested lists.
All right, part 1, the Python sequence, laying the foundation.
So right at the very foundation of how Python stores data, we have sequences. Literally everything else we're going to talk about today is built squarely on top of this one fundamental building block. Simply put, a sequence is basically just an object that holds multiple items of data, stored one right after the other. It's kind of like a highly organized container. Instead of creating, say, 100 totally separate variables for 100 different test scores, you just create one sequence. It keeps the whole shebang in a reliable, predictable order.
Now, Python actually gives us two primary flavors of these sequences, lists and tuples. And really, the key difference here boils down to mutability. Lists are mutable. They're this open, active toolbox where you can add, remove, or change things dynamically on the fly. Tuples, on the other hand, are immutable. Once you create them, their contents are locked up tight, like a sealed vault. No changes allowed.
Moving right along to Section 2, navigating and slicing data, looking inside the box.
Okay, look at how Python numbers its positions here. Up top, you'll notice that indexing starts at 0, not 1. Classic programming, right? But the real brilliance? That's on the bottom row, negative indexing. Say you want the very last item, but you have absolutely no clue how long the list actually is. Just ask for index -1. It is such a clever, incredibly useful way to just work backwards without overthinking it.
Finding just one item is great and all, but what if you need a whole chunk of data? Well, that's exactly where slicing comes in. A slice is simply a span of consecutive items taken directly from a sequence. It's absolutely perfect for those times when you need, say, just the first 5 days of sales data, or maybe just the middle 3 test scores.
So, let's break down the actual anatomy of a slice. Step 1 is your basic syntax. Start index, end index. And remember, Python grabs everything up to, but not including, that end index. Step 2 levels things up a bit with a step value. You can actually skip elements just by tossing in a second colon. And then step 3 really shows off Python's flexibility. If you just omit the start or end indices altogether, Python automatically defaults to the very beginning or the very end of the list for you.
All right, Section 3, the List Manipulation Toolkit, active verbs.
Because lists are mutable, we can change them up. I actually like to think of list methods as rapid, action-oriented verbs that just transform our data on the fly. Let's rattle off this cheat sheet. We've got append, which just slaps a brand new item right onto the end of your list. There's index, which searches the list and tells you exactly where a specific item lives. Need to squeeze something into the middle? Use insert. To organize chaotic data from lowest to highest, you just call sort. If you got to get rid of something entirely, remove finds it and deletes it. And reverse, well, it simply flips the entire list completely backwards. Every single one of these commands actively alters our mutable toolbox in real time. It's literally reshaping our data structure with just a single line of code.
But wait, here is a massive trap you need to watch out for. Typing list2 equals list1, that doesn't actually make a copy. It really just creates two name tags pointing to the exact same list in memory. So if you change one, the other changes too. To safely create a totally separate, identical copy, you want to use concatenation. By adding an empty list to your current list, you're essentially forcing Python to build a brand new, independent list in memory.
Which brings us to Section 4, processing real-world data, the toolkit in action.
So why do we actually learn all these methods? To solve real problems, obviously. Take Megan, for instance. She owns a small neighborhood coffee shop, employs 6 baristas who all make the exact same hourly rate, and she needs to calculate payroll. Combining a list with a loop solves this whole thing seamlessly. We start by creating a list with 6 zeros. Then, using a loop, we prompt the user for the hours worked by employee 1, then employee 2, and so on, overwriting those zeros with the actual real data. Once the list is full of those hours, a second loop just multiplies each list element by the pay rate to figure out the team's gross pay. It's clean, it's efficient, and honestly, if Megan hires 2 more people tomorrow, she just changes one constant variable and the whole program adapts instantly.
Or let's look at Dr. Leclerc's chemistry class. She drops the lowest test score when averaging her exams. First, you get all the scores into a list. Second, you get the total. Third, and this is really where Python shines, you just use the built-in min function to instantly find that lowest score. Subtract that out and calculate your average. Leveraging built-in functions like this makes processing complex real-world rules just incredibly efficient.
And finally, Section 5, Going 2D, Nested Lists.
All right, now for the real climax of this explainer, the slightly mind-bending concept of lists nested inside of other lists. Because a list can hold virtually any data type, it makes sense that it can hold, well, another list. In this student's list here, each of the 3 elements is itself a list of 2 strings. So student 0 isn't just the string Joe, it's that entire inner list of Joe and Kim. Welcome to 2 dimensions, folks.
This usually creates a massive aha moment when you actually map it out visually. A 2-dimensional list is really just a grid. It has rows and it has columns. Think about it. If you're tracking 3 students and each student takes 3 exams, you just need a 3x3 grid. To navigate around it, you simply use 2 subscripts right side by side. The first bracket selects the row, so the student, and the second bracket selects the column, that student's specific exam score. By utilizing nested loops, you can process entire massive spreadsheets of data with just a handful of lines of code. It's a total game changer. Which leaves us with a final, kind of fascinating thought. If a list can hold another list to create 2 dimensions, what happens if that nested list holds another list? 3 dimensions? 4? I mean, really, how deep can the data rabbit hole actually go? The answer is literally limited only by your computer's memory and your own imagination. Python's data sequences offer this incredibly dynamic, totally expansive toolkit. I really hope this explainer has left you eager to get your hands dirty and experiment with multidimensional data and list manipulation yourself. Keep exploring and happy coding.